It's because there's a whole bunch of things that either I promised some of you to talk about, or I didn't get time to talk in the previous two lectures. Do stop me at any point if you have questions. There's tons of things I want to say today, and towards the end, I probably will kind of throw you off, coming from left field with a crazy thought. But I think it's one of these things that we can do if we take seriously the theory as a nonlinear theory, and then what surprises might linger in there. So let's start. I'll just say a few things that kind of I didn't get to in the past few lectures, and then move on to what I want to say today. So as I said, we have been discussing quite a bit about black holes. Just at the very end of the last lecture, I said something about what happened with when you open, but I just want to kind of give you a glimpse of some of the things you might have to deal with if you open the door to think considering beyond just black holes. Of course, black holes are in vacuum, then everything we said the first day essentially gives you the basic tools to try and simulate black holes. But the moment you open the door to having sources, then you have to worry about how to treat those sources, and where you can use the same kind of techniques that we discussed, or maybe you need to think of a few other ones. So suppose you are dealing with scalar or vector massless or massive fields, which may be minimally or non-minimally coupled. And we're going to discuss a little bit of one example that is non-minimally coupled. But by and large, if you study these kind of objects, with the exception, say, of neutron stars, the techniques we discussed in these past few days are equally applicable. Like, why? Because you have the same type of equations, that these equations we call linearly degenerate. So the standard arguments still apply as long as you have a hyperbolic system, which may or may not be obvious at the very onset. But if you choose the right gauges, you do the right, perhaps, combination, massaging of the equations, then it is hyperbolic and system. And the main lesson that we got the first day is that as long as you have a symmetric or strongly hyperbolic system, you can always picture that what you're dealing with is just a sequence of advections equations, and may or may not be more complicated than by the lower order terms. But by and large, everything that we discussed will apply. And the beautiful thing of that is that we can rely on applied mathematical techniques or theorems that have been developed in the late 90s and the early 2000s that basically tell us if you have a system that is hyperbolic with the good hyperbolic properties, and if you discretize the problem this way and you use this type of iteration, you're guaranteed to have a well-behaved numerical code. I mean, that's a very, very strong statement. It usually, if you open books in that typically physicists write, prior to the 1990s, numerical techniques seem to be a little bit of a art magic, and black magic and art, that people trying to say, well, this combination works, and never explaining why. That is all stuff. Nowadays, one can go and plow ahead with very strong backing by real theorems coming from applied mathematics. If you, however, want to then study neutron stars, well, you have to start adding new physics, a lot more new physics. You have to think, what is the matter that you're going to be describing? How is this described? It might have phase transitions or not. It may be magnetized or not. Someone has to provide for you the equation of state, because after all, this is one of the things you want to do, to try and understand or get a hint from gravitational waves what these neutron stars may be made of. And then you might have a whole bunch of other physical effects that you may need to incorporate. And we heard from Adam yesterday, all the amount of physics that need to be incorporated in that problem, core collapse, because you're talking about very, very long time scales where everything can play a significant role. So I'll just say a couple of slides of what happens the moment you start introducing this type of phenomena or this type of ingredient. Remember, we discussed about equations that are truly nonlinear from the point of view of mathematics, which is equations that in kind of the right-hand side of your evolution, you may have terms that go like, have the speed that depends on the velocity, on the state of your field at the same time. So this is what can give rise to shock. So if you have in here like u squared, then you can act with the derivatives would be, you could write as u comma x with a factor of 2. And then you might think that that's an equation that is similar enough to the ones you've described, that you can just use the techniques that we mentioned. But the problem is that this one will give shock. So it literally could have discontinuities or very, very large gradients. And then how do you deal with that? So just as a very short primer, in case you deal with this and you know what the right resources that you may look for are talking about, then the way you're going to treat those problems is first, you're going to try and write them in conservation forms. And this is why instead of writing dx or u comma x times 2, you want to write it this way. The derivative, or like a derivative of some flux, here you'll put u squared. And then you're going to understand this equation or solution to these equations that you know could be discontinuous in a weak sense. So you imagine that you multiply by a trial function, you iterate over a space-time volume, and then you try and make up from there the right pieces of the solution. So for instance, if you iterate this equation here, then you can make sense of the first piece as a time, like this iterative volume. Then this will be the rate of change of how the amount of, say, this quantity u at a given time changes from this slice to the next one. And that's going to change by the amount of flux that enter or leave that domain from the boundaries of that domain. And so then this is how you're going to understand the iterating by the system. And you're going to allow yourself the possibility that at that interface, the solution wants to have two different values. You might have a value from the left, a value from the right. Again, imagine you're driving on the highway, someone slams the brakes, all of a sudden there's this pile of cars. Well, there's a huge density behind that idiot that might have slammed on the brakes and a very low density in the front. And then you have to understand which way it is going to move. Is it going to move to the left or is it going to move to the right? And then you're going to react, or the numerical simulation will have to react to that. And so there is a so-called Riemann problem, which precisely sets that situation for you, given a problem that can have these discontinuities. You want to understand in this weak sense, what is the solution to a state where to the left of some interface, the solution or the function that you're dealing with has a given value and a different on the other one. And depending on the characteristics of your problem, out of that, you're going to construct that unique solution that maximizes the change of entropy, and that's a physically correct one. So that was just a very quick kind of overview of the type of ingredients you have to deal with when you are dealing with this truly nonlinear system of equations. And every time you see binary neutron star simulation, that is going on in the background for the hydrodynamical fields, for the fields describing the star. Everything else is, for the metric, is described in the standard way we said. One other thing you would mention is, notice here, what you are seeking for is to write your equation of motion. Maybe there will be a source in this form. It's like the derivative of some, or the divergence of some vector, and these are the fluxes. That what that translates in the context of numerical relativity simulations is to defining new variables, which are called conservative variables. These are the variables that combine several of the variables that describe the state of your matter, but such that they allow you to write the equations in this conservative form. And as a result, then there are very intrinsic, very complicated ways from going to conservative to the primitive variables and vice versa. And this, in and on itself, is one of the really complicated parts of every single code that does matter dynamics. So that is a little bit of information on these methods that are high resolution shock capturing methods, which actually do precisely that. Assume that at any interface, there could be a discontinuity. If there isn't, then you treat things in a smooth manner and high accuracy. But if there is a discontinuity, then you adapt the system in a particular way. That involves everything we discussed: understanding the characteristics, understanding the potential jump, understanding which way things are going to move, and from there, obtain how the solution is changing from one step to the next one. And a useful and nice resource is this book by Levesque that contains a very good description. Say again? Sorry.
Is it obvious that all the nonlinear stuff can always be written as this divergence. Is this some ask about the physical problem?
No, great question. Is it always possible? Yes. Is it always possible that you're going to have a zero in here? No. And that's a key observation. Thanks, Matthias, for the question. So as long as you have a zero here, then this theorem of the Riemann, solving the Riemann shock truth problem, tells you that this is a way to get the unique solution that is the correct physical one. The moment you have a source here, then it's not so clear anymore. So in the context of general relativistic hydrodynamic applications, many sources do show up, but this is the best you have. So you pay the price, and so you put in here as much as you need to be able to write this as the divergence of a flux vector, and everything you cannot, then you move to the right-hand side. And I think on the first class, on the first lecture, I made a comment in passing that I said, for all of you that might know this, in the context of magnetized matter, people use ideal MHD equations. If you look at the ideal MHD equations that are in the way they're typically treated, they have a weakly hyperbolic system of equations, which I said this is very dangerous. And if you throw in the constraint, the monopole constraint in the right-hand side in the appropriate equations, then you can write it in this way. Then now you have a system that is weakly, that is strongly hyperbolic, but the price you paid is to have some new sources. And so that depends on what Poisson you want to get. Either the Poisson is that you need to deal with a weakly hyperbolic system of equations, which you cure by enforcing the constraint actively by this complicated constraint transport that I mentioned in the second class, or that you add some sources and then you continuously monitor that the solution is well behaved. Thanks. So now I'm going to go a little bit beyond GR, because it will give me the excuse to both say what happened when everything we discuss doesn't work. And then you have to get creative. And maybe then at the end, I'm going to slowly lead us back into the gravitational wave from binary black holes and then try to ask some fun questions. Well, fun for me. So if you're going to open to go beyond generativity, what does it mean to go beyond generativity? Well, it might mean beyond the theory itself or beyond the compact objects themselves. So I'll say much more about going beyond the theory, but maybe we can discuss a few other things. Of course, if you try and open the box to beyond generativity, you want to ask why do you want to do it? So one option might be, well, we are concerned about the information paradox. You don't know why the black hole would have such the entropy that we think it has. And so then these issues bother you so much that you want to replace the black hole with something else. Well, what is the something else? Given the black hole is a non-local object, well, you may have to introduce some non-local operator into your theory to try and represent that. But if you are successful in doing that, then you could argue a black hole of size 1 and a black hole of size 1,000,000 will be changing about the same way. So it doesn't matter how large the compact object we're talking about, whether we are accessing the local neighborhood of one of these objects through gravitational waves with, say, LAGO, Virgo, Kagra, and therefore we're dealing with stellar mass objects, or we're dealing with maybe EHT observations of the supermassive black holes in the universe, or we do it with PTAs or LISA. You would imagine that the way this black hole or this non-black hole now behaves is the same way as a larger one, and so there is not really a scale associated to the mass of that object, maybe with the exception of the scale, if you want, above the horizon of which you begin to be sensible to the fact that this is not a black hole. Alternatively, you can say, well, we're going to build in a different way. We build a theory based on the Ricci scalar, which is a curvature measurement, if you want. So you might want to say, well, if there are corrections, I could try and build a theory that changes it in a gradient expansion form, so higher orders of the power. So an example, again, I'm going to keep talking about my water. If you use your other equations to try and describe water, that's fine, but they don't include the effect of dissipation. But then you can say, what can I construct that are higher order gradients of the variables of my fluid that will account for energy loss in the system and entropy growth? And this is how you write, well, you throw in some transport coefficients, which is a measure of your unknown physics. multiplying the gradients of, say, the velocities, and that will give you a sense of, oh, this is how I can add viscosity to the system. So you could imagine doing the same thing for gravity. So you say, well, my leading order is the Einstein-Hilbert action, and I'm going to add higher order powers of the curvature to account for new physical effects that come from higher energy fields or processes that somehow percolate and can be represented in this way. Very much like the viscosity terms that I added to my earlier equations to arrive at Navier-Stokes equations. And those terms basically are telling you how molecules in the fluid collide with each other and lose energy that way. Or maybe you want to give up some of the basic tenets of the symmetry, and you're ready to give up some symmetry. So you typically, because I was in this camp, you would have kind of this dialogue. Someone would come to you, oh, you do numerical relativity. I have this cool theory. And then because you have been hurt more than once dealing with things that were not well behaved, you would ask, well, is it well posed with respect to problems you're interested in? I said, well, I don't know, but if not, then remember, it's only valid where applicable. I said, well, but what if it naturally leaves that domain? Well, I would say bummer. But then what do you have? I have this cool theory. And this goes in circles. And we didn't get much progress until some of us said, well, let's just try and take a look at what you guys want us to do, and then we'll see where we go. So in many respects, we are kind of in a deja vu state. Prior to the numerical simulations being able to resolve the binary black hole collisions, you would have this plot. This is a plot that is attributed to Keith Thorns. There's some lecture notes. So, well, earlier on, you have this spiral. We know what will happen. At late time, we think we know what will happen because we expect this space-time to decay to a curved black hole. And here we can use quasi-normal modes. And in between, well, we don't know what it is. Eventually, numerical simulations will deal with that. So we are kind of like that when we open beyond GR theory, but not so much because we have detections. I mean, so whatever we can dream of better be consistent with observations. And the observations are very consistent with general relativity all through. So whatever is changing things in here, it better not be fundamentally different. Or we should have a strong principle to say this transition will be very smooth. And I will argue about this at the very end. So as you open that door, you will see different type of complexities coming in. So the first one is, and I'm just going to motivate with some theories. I'm going to describe some particular processes, and then connect that kind of observations with other options that people are entertaining, and hopefully give you some pointers as well as to what you might do if you're trying to use numerical simulations to explore some of these theories. So suppose one type of theories you can imagine dealing with are such that they add one extra degree of freedom, and that is non-minimally coupled to gravity. So an example is this one. This is the so-called Scalar-tensor theory introduced by Damour and Esposito Fares. This is the one that is strongly tested to some degree by binary pulsars, and I'll tell you why in a second. Then you can write that theory and then minimal couple y, because here you have this new scalar degree of freedom that has been thrown in, multiplying your Ricci tensor. And so you're going to expect some new phenomenology due to this. You can do a conformal transformation, go to a different frame called the Einstein frame, and then write it in such a way that the Ricci now shows up clean, but you have a non-trivial coupling to the scalar fields. And then if you have some matter, then the matter now in this new transformed field will obey some weird things in that it's not following geodesics of the original metric, but it's following geodesic if you were a particle of this conformally related metric. And if you add an extra gauge field, then you would have this theory, but it's about the same. So at the bottom level, it's okay, what can you do with that? If you study what the equations of motions are, the equations of motion in this theory are not too complicated. The Einstein equations are the same, adding some stationary tensor for the scalar field and maybe the matter. Then the matter will have its own evolution, and so will with some coupling. But the important or the interesting thing is this equation is the equation that the scalar field will obey. And there is a coupling now with the matter. And so then this is proportional to phi, think about it. And depending on the size of the stress energy, the trace of the stress energy tensor, what you can have here is a tachyon. So you can have a box phi with an effective mass of the system, which would be negative, so we'll grow a non-trivial solution. And so this is something that was recognized from day one by the proposers of this theory, and this is called this phenomenon of spontaneous scalarization. You could have a star that is has a sufficiently strong stress energy tensor that will induce this scalar hair. So if you were an observer at infinity, you would not think that the mass of the star is what it had before, but now it has some extra mass associated to this hair. And this is very similar to what some theories give for the case of black holes. This theory, the coupling is with matter. So if the matter is absent, if you're in vacuum, it gives exactly the same behavior for black holes as it gives in general relativity. But people are clever and then find ways to kind of see the same kind of phenomena with appropriate couplings between the scalar field and the curvature in the case of black holes. So there is another kind of story that very much plays the same way as this one. So what new things you have associated to these theories? Well, new things come. If you have now an object that has some scalar hair associated to it, then you can have this interaction radiate dipole radiation. And so not only you can have your system governed by quadrupolar radiation from the system as expected in general relativity, but there is this other component that if it is strongly enough, as far as the charges that you induce in the scalar field, then it can radiate very effectively in the dipole and actually dominate at some point. So the two leading order, and then you end up with this type of dipolar radiation, which is kind of an interesting observation that the dipole will be related to these scalar charges that you are inducing. But if you have an equal mass system, the dipole charges are exactly the same. So this is not there. And then you wouldn't have an observation. For all intern purposes, what you have is just a system where the masses have been regularized. But if there is a little bit of mass asymmetry, then this one will induce a faster decay of the orbit. And these are just some putative examples. It doesn't matter. You can see maybe close to merger, clear differences between the strains in one and the other one. After merger, if you look at the fundamental modes of oscillation of the after merger object, if it hasn't collapsed into a black hole right away, you can see the impact of them. But this is just some examples. So basically here I'm going to pause. And this is so good at what we can calculate with now new issues. There's a subset of classes that satisfy this. The introduction of new physics has not thrown anything out of the beautiful or all the properties that we demanded a sensible theory to have. But now let's start peeling off that onion and throwing things away. So one thing, for instance, you can say, give up full Lorentz invariance. This theory, Einstein ether or Hosheva-Lifshitz does that. So you end up with a theory that is highly complex, that involves not only the metric, but there is a perfect vector field that you have to evolve. And it's not 100% clear how well to treat this type of equations. There is some good, interesting work by Olivier Sarbach and collaborators recently in defining at least the initial boundary value problem in a sensible way. I'm not going to talk about this, but this is one example. This is one of the most radical examples, if you want. But now let's do black holes in quadratic gravity. So we're going to use this kind of effective field theory approach. Just as I said, when we go from Navier-Stokes or Euler's to Navier-Stokes, we add extra degree of freedom, and we add extra gradients to account for the extra physics. You can do the same thing in gravity. So imagine you have this your Einstein-Hilbert axion, and then you say, well, I'm going to try and include higher order powers of the curvature to account for corrections. I can start with R squared, but if I go to R squared, there is a theorem by Lovelock that says it better be that we have it coupled with something else. Otherwise, in vacuum, it doesn't introduce anything. So you're going to throw in some extra fields. So you can have extra scalar fields here, there. And then what you're writing is the most general combination of squares of your Riemann or your curvature tensors. So you add all this. Doesn't matter. Don't look for the details. I'm not going to be advocating for any particular theory. I don't think there is a chance to do that. But we're going to be looking for trouble. So what things may be lurking in these theories that might complicate your life if you want to do a numerical study. And you want to do a numerical study because these theories are so complicated that in order to kind of get some headway into what the dynamics might be, you have to put in the computer, but because you don't have the right properties, putting in the computer might be a very complicated task. So let's just count derivatives. So we're going to do that very simple task. So we get the equation of motion. We're here. This signs the equation with the stress energy tensor associated to the scalar fields that we're adding. But then we have this kind of extra contribution to the equation of motion that is of this shape for the case where we're studying, let's say, this piece. So it's a scalar field coupled with a Riemann square. And then I come here, I have the Ricci tensor here. I know I have two derivatives. And then I have two derivatives of the scalar field. And so I have four derivatives in the right-hand side. And in particular, remember I said, if you talk with your mathematician friend and you have an equation of motion where you have u comma t equal u comma xx times u comma xx, they will look at you as there is something wrong. Well, this is precisely what you're seeing here. And I'll show you some of the problems that could lead to explicitly in a second. Let's look at another one, dynamic at Chern-Simons. People entertain that. Let's look at this piece now. So if we look at that piece, then let's count again. We have that term that comes in the action and the equation of motion, and then we come here. Oops, there is a derivative of the Riemann. So we have first derivative of the scalar field times third derivative of our metric field. So we have now an issue. So we had an equation that was box, let's say, of the field. Now in the right-hand side, we have three derivatives. And in particular, we might have three time derivatives. Because now what do we do? If you remember your Abraham-Lorentz force of a particle that is charged, that is moving through a medium that have an electric field, you have kind of that behavior. You have the Newton's second law will say the acceleration is related to the jerk. Already that in itself gives you a delicate equation to deal with. And that's an ODE. Imagine having that with a PD. So again, what do you do here? Where is part of the problem? Part of the problem is a dialogue problem. Everything I said with understanding the properties of the equation of motion, the part that comes, of course, from the partial differential equation theory, comes from trying to understand the well-posedness of the problem. And in particular, what you try and do there is ask, what happens in the high frequency regime? In the infinite frequency regime, do you have control of your solution? But the EFT approach doesn't want you to do that. It's that the EFT says, if you're in a regime where higher order gradients are subleading with respect to lower derivatives, we can write this. If you want to ask what happens in the high frequency regime, you're not allowed to ask this question. You're not allowed to say, I want to know what happens in the high frequency regime of a theory that was written assuming you never are in that regime. So that it's already an issue. It's a physicist kind of getting in trouble with the mathematician and so vice versa. So how do you do that? So you're trying to avoid this, and somehow you're trying to think of in this way. So imagine soap bubbles. They're very nicely described by Navier-Stokes. Start pulling them apart. At some point, the neck or the area where maximum shrinkage begins to be small enough that has length scales also commensurate with those of the molecular dynamic scale. So there, that theory doesn't work anymore. You cannot ask Navier-Stokes questions there. Somehow, then, if this kind of say, you keep doing it, it breaks. The dynamics is described by something else in Navier-Stokes. And then the system kind of smooths itself out. And then these pieces can be described again by Navier-Stokes. So what we're trying to do, if we end up getting this regime, we need something that allows us to kind of bridge one region to another, or at least we need a tool to try and get sufficiently close to know that this happens. And if this happens naturally, we then can do one or two things. One is to say to the theory where it came from, you need something else to describe this scenario. And also, you might end up saying, well, this kind of behavior will produce such a radical correction of the waveform that we can already rule it out. but we need tools for that. And this is something that the community has recently, in the very recent years, kind of found ways through. Before it was just hope. So I'll tell you what these are. In spite of all that, people have written tons. For many of these theories have written black holes. They have said that, or shown that these black holes differ from those in GR. For instance, in Einstein's Gauss-Bonnet, you can find solutions that describe rotating black holes, those which are different from those of Kerr. So that already tells you something. And then if you analyze, say, the quasi-normal decay of perturbations of those black holes, they differ in some degree to those the Kerr solution, and then you can go after potential dose deviations in the data. We like to know, of course, if they are stable, because if they are not, then we shouldn't even be bothering. Want to understand the dynamic behavior, how they relax to equilibrium. This relates to these quasi-normal modes. Do they relax in a faster or slower way? What is the final state, and how do we interact with potential other fields? Because as I said the other day, for instance, you have superradiance in generativity in Kerr that grows clouds around the black holes, and then you have really potential connections with observation. So maybe in these theories, that behavior is not only there, but more radical. Is in an axiom for GR is well posed. How do I answer that? I mean, I don't think people were writing that theory. I don't think Einstein was writing that theory thinking of where it was well posed or not. In fact, we didn't know that for 40 years after the theory. I think, also the concept of well-posedness, it's about the same time. I think so Hadamard did it in the early 1900s. So I'm not sure physicists understood that very well that. But now we do. And we do understand that, like, either a theory is well posed, in which case you can say, well, this is a physical theory. And if it's not, then we should understand in which regime it is. So one thing that I can make a comment that would be useful later, like GR has this weird thing, right? So GR hides in itself two extremes. Like, we know stability of Minkowski, so we know regimes where we perturb it a little bit, and it's just perfectly sound. So if I imagine an effective field theory point of view there, it would be perfectly sound to work there. In the R case, we also know that GR has the right scenarios lead to singularity formation, and then everything breaks loose. But then GR kind of goes around and says, oh, I'm going to have a black hole, and I'm going to let you get away with murder. So maybe all these theories, when this thing is about to break, do so hidden inside of an event horizon. That's something you would like to know. But we know now that's not the case in some of these theories.
So GR is the unique theory of a massless field proof.
Yes.
That is unique.
Yeah.
So it would be strange that a world that contains a massless field, it cannot be described by any theory that is well posed. How could this possibly be?
It cannot be described by a theory.
Yeah, you say somehow we see that there's massless field in the true field, and we know the only theory that is consistent with Lorentz event is GR. But then how could it be that it would be imposed? There would be no solution.
Oh, I see what you're saying. Yeah.
Because it's the only thing we can possibly predict. So.
I mean,
then the world would not be mathematically described. I mean, something like that.
I agree with you, but of course you know that if you take that to the extreme when singularities are about to form, then okay, there it's breaking. And we didn't have who order that the black hole will always come to the rescue.
There is an effective theory would be something else.
Sure, okay. No, I'm with you,
You're saying that it would only be well posed if there is an additional scale. For example.
Yeah, these are interesting questions. Okay, so sometimes also they are underappreciated issues, and we all underappreciate that. Sometimes there is this concept of linearization stability, and I think you have to be old there, at least as Matthias and I, to know this thing. In the context of cosmology, this was discussed forever, right? You remember the discussion, Matthias? Like, it is not clear a priori that the solution to the linearized equations of any system are the same as the solution to the full problem in the linearized regime. And this was, there was tons of discussion in the context of cosmology, of course, because in cosmology you deal with linearized perturbations. And then, well, is that informative to the truth theory? So this is a delicate question. I'll give you an example. Take Navier-Stokes. So I keep going at the fluid. There is a theme here today. If you think I'm going to linearize the problem, so that you have two options. You're going to linearize with respect to the velocities, in which case, then your equation is the rate of change of the velocity equal, the next term is v dv, so you're throwing that away. And then the next term is a dissipation. So in this case, you're going to say that's just completely decay. You can instead linearize with respect to gradients, in which case you throw away the dissipation because that's second order. And then you have dt vis-a-vis. And then you will say, well, the behavior is always nonlinear. And you know the truth is somewhere in between. So it's careful. One has to be careful when saying, oh, I'm going to study this problem in the linear regime, and that is informative to the full problem. That's a tricky thing. And I already talked about this. There is also an overappreciated issue that, and then there is a huge family of beyond general theory theories that went out of their way to try and write second order equations. And so, well, one principle that might guide your search for a new theory is to say, whatever I write has to be second order in nature with respect to the equation of motion. And let me just not write about this. Well, I'll say it. And then you say, well, maybe I can think of it as particle physicist. Maybe my equations are not second order, but I will treat the part of JR as the one I care about. The R1 is a small correction. And I can always evaluate it iteratively by the solution I find. If I turn off the corrections, I get a solution and I plug it in there. But that might not be good enough. And I can give you a simple example of why not. But let me move on. So I'll give you one example. This is one of these theories, or is this theory, the most general theory. In 4 dimensions I can write that will give rise to second order equations of motion. This is something, it's a work by Horlensky. And then you have these complicated things. Forget about the details. I'll just show you an example. So if you take one case of that, you do this transformation, this conformal transformation to write Einstein's equations in the best possible way, but then you mess up the scalar equation. You end up with this theory or this equation. It's a complicated thing. Forget about everything except this piece. So here, this is the second derivative of the scalar field multiplied by your matrix. So that's your box equation for the scalar field. But then you also have this. And now notice what you have is the second order of the field times the product of the first order of the field in here. So that already tells us we had an equation that was well posed, or otherwise we wouldn't have shocks. Now we will have shocks. Not only that, it could even completely change the character of the equation. We might have something that's hyperbolic if this were not there. But the moment this begins to kind of grow, it will change behavior from hyperbolic to elliptic, and indeed it does. So if the coupling is sufficiently strong, or if you're in a regime where you're letting something collapse on in and on itself, then at some point the initial value problem just breaks down completely. And this is where this dialogue I had at the very beginning, so the person that proposed this was a bummer. It is what it is. I mean, in the regime of a collapse, it will abound on the FT theory. This should be something else that we write for it. Okay. But if you're not in that regime, you can ask, how is that affecting my merger of black holes? And this is an example by these authors where you can write that system of equations in the right way by manipulating sufficiently in a way that is locally well posed, and you can find solutions, but if the coupling is sufficiently large enough, then everything breaks down. So just some phenomenologies of these theories, and black holes would have scalar hair. The rotation black hole is different from those of Kerr, as I said. And then the question is, okay, suppose you now are happy and you say, well, within a regime of the coupling strength, I'm happy with this theory. I'm going to explore. I'm going to put that bound, given that I have the solutions, given I have gravitational waves that tell me what the shape should be. I can go and constrain based on that up to a maximum level of the coupling. But then, of course, the question that hinges at the end is, can we form black holes? As you form, then you explore sufficiently large curvatures that this might be in the regime that things blow up. So there is a way to do precisely the example I mentioned before of a soap bubble that breaks into two by changing this theory ever so slightly, and I'll give you some of the details. And indeed, you can find a regime where this theory will break if you don't do anything, and if you change it in a slight way that ensures well-poses all the way through, you indeed find the collapse, and the collapse agrees with the black hole solution that you would have obtained within the right regime. So there are two problems, and I'll show you these two. Let me just go back a little bit to this. Oh, okay. So now we're going to try and deal with two problems at once. So either we have something in the second order, but it can change character, or we can have things that are higher order, and there we don't know what to do. So the last few years, a couple of ideas have come out. So let me describe the first one. Suppose you have this theory. Forget about this extra term. So you had like a free field. You know what that equation of motion for this would be. It's just a box phi, let's say, equal to 0. Suppose your theory, you're trying to account for some extra physics that you didn't have, but you're trying to say, well, there's some beyond my free field. You could imagine, using whatever principles of symmetry, that the thing you're going to modify with is this. So it's the next, this scales like 1 over length squared, this scale like 1 over length to the 4th. So if that's the action you take, the equation of motion would be up to here. So this piece will add this too. This is not too bad, but this is exactly the type of the one that we're just discussing. Here we have a second derivative of the field, which will be part of your principal part. But because it's multiplied by the gradients, then this combined thing can end up changing the character of your equations, and you cannot evolve it. But now what you can do is kind of undo some of the work that you would have done in EFT. If you take your EFT hat seriously, you would not have considered this term. This is a term, like gradient of phi, gradient of the box of phi. This is a term that can be field redefined away. So if you imagine doing a field redefinition of this form, phi equal phi plus alpha grad phi, and you plug it in here, if you didn't have it, you can put it in by this definition, or if you have it, then you can throw it away by making introducing this type of transformation. And the standard way is that when you write your effective field theory, you try and write the most general one containing all terms up to everything that you can throw away from field redefinitions. But these gentlemen have brought this back in for a good reason. So if you now introduce these, the equation of motion contribution of this term will be of this form. So now look at what you have. We have box of phi, we have this thing, and then we have box of phi. So we have 4 derivatives here. As far as the scaling is concerned, this thing scales in the same ways as that one. It's 1 over L squared, 1 over L, 1 over L. It's 1 over L to the 4th combined. And this is 1 over L to the 4th. But if you now ask, what is the property of your system of equations? Now remember what we said the first day. Look at the highest derivative of your equation, and then check what they are and what properties that operator has. So the highest derivatives are here. All of a sudden, these, which was something that shouldn't have been there in the first place, come in, and it's the one that dominates your analysis. If you ask that is sufficiently hyperbolic, then the answer is no, it's weakly hyperbolic. But you can also ask now that, remember what being weakly hyperbolic meant. Is if it is weakly hyperbolic, whether the problem will be well posed or not depends on the lower order derivatives. So we like strongly hyperbolic because then we don't have to worry about those. But if we do have to worry about those, then you can go and check them. And then in this case, it's very easy work to check that indeed this is well posed. What you have done is introduce a new field, imagine the box of phi, which is massive. So you end up with a massless field that you had originally, and another set of fields that are massive, and they behave in the right way to restore well-posedness for you. If you play too strong with this, it might end up modifying the solution, but it's a way to at least get in the game of saying, now I can put it in the computer and try to study it. Yes? Right, and so now is where it also depends on how rigorously, you're going to play your EFT game. If you're going to play your EFT game rigorously, you're going to say this guy has to be of order that guy. Ideally, because this alpha is going to be essentially given the mass of this new field, and you don't want this, because you work hard and somehow you feel that this is what you want to study, and you have thrown that in. What you like this one to be sufficiently smaller than that one, because this, you'd say, with this massive field, it has a very large mass, and it's very hard to move it around. So as long as, but I can tell you, so as long as you choose them about the same or even smaller, then the solution for small enough couplings do not seem to be significantly affected.
Does that just mean that when you are there, you can always rewrite the action in terms of the field, and it just looks like some here is not like so it will be equal.
Say it again. Can you repeat?
You have written a field prediction there.
Yeah.
So if you do that, then you succeed into the action. Does the action become something that is manifestly non-highly derivative?
Manifestly? No, so here I'm just playing, maybe I'm not exactly getting your question. So here I'm just playing, the only game I'm saying is that I'm changing at this level. I want to add something that is at most at the same level that will give me a higher order operator that is sane, that will ensure that the highest derivative, the one that if I want to talk with my mathematician friends that tell me on the PDE side, you need to have the higher order operator to be well behaved, I can ensure that. You could have done something else. You could have done phi alpha box of phi, let's say. You could have done that. You plug it in here, and then you would have generated a box cube. That still is fine. It would have been more costly, but you can also do it. But then the question is, well, if you're now putting something that scales like the cube of your operator, why didn't you put something, the cube of that is consistent with here? But again, this is where we end up in the circular loop. As long as you are in the EFT regime, this should be subleading, and then you can keep going. I'll give you another route. This is another one that it's more pedestrian, but it also gets the job done. And I will connect with the comment I made the first day. So when we talk about parabolic equations are not to be found in general relativity, and this is something that Geroch, as long as you're talking about the evolution of this. And Bob Geroch pointed out many years ago, so suppose you have the heat equation. So this equation is just a heat equation written in terms of an extra variable. U, T is some constant. Then you have the gradient of Q, but Q happens to be the gradient of U. So this is just your standard heat equation. So Bob said, well, promote this equation, change it to that. So you have an equation that says, in a time scale given by tau, make Q exponentially converge to the gradient of U. If you study this system, now this system is hyperbolic, has finite propagation speeds associated with this tau, and it's a way to kind of make a parabolic equation in the long wavelength regime be hyperbolic, and the high frequency regime, you say, I'm not going to bother about that, I'm going to dissipate all the way. That's what this equation is doing. So you could imagine doing the trick very much like that. Imagine this kind of problem where you have this, and this could have an arbitrary number of derivatives. It doesn't matter for this particular example, I'm just giving this. And by the way, if you don't know who this is, you're missing something in life. So this is a wave equation, but with an extra term, and I can even change this to a negative sign and make and the -2 and force it to be elliptic. But you want to say, well, if U is sufficiently small in the gradients, I can then try and force it to study hyperbolically, and then you introduce a new variable, you give an evolution equation to that variable that exponentially forces pi to decay to that one, and then you can see that this is a way to deal with this problem. And this is very much the same way that people in relativistic hydrodynamics, in the context of quark-gluon plasma collisions, deal with this. So remember I said, if we take our fluid, I've finished that water, so I'm going to start this one. If you start with Euler equations and you add the viscous terms, then you end up with Navier-Stokes equations. You can do the same thing with relativistic hydrodynamics. We have perfect fluid, you add the viscous operators, and if you ask what are the equations of motion now you're in trouble. Those equations are not well posed. you have tachyons, you have faster than light propagation speed, all hell breaks loose. But people like Werner Israel and Jim Stewart came to that problem, introduced kind of a trick inspired by this kind of construction, and you can fix the Navier-Stokes equations in the so-called Israel-Stewart formulation. And this is what people use in the context of, say, quark-gluon plasma studies to be able to use relativistic hydrodynamics in a controlled way that has the viscous dissipation accounted for. Nowadays, there are other ways, but this is something you can do. So this is an example of trying to go after this equation or this theory. So quadratic gravity, you imagine your action is given by the Einstein contribution plus operators that go Riemann to the fourth power. So if you write down the equation of motion of that, you imagine that you can easily imagine there are very high derivatives. Then how do you deal with that? So you can take a page out of that trick, and this is something that we did with Ramiro Calloso, Pau Figueira, Santiago Franca recently, where you add an extra degree of freedom to do exactly the kind of trick a la Geroch, and then now you can study that theory. And in particular, this is an example of a binary black hole collision where the coupling has been chosen to large enough values for it to kind of show a significant difference. And where you have a positive or negative will mean an acceleration of the collision, so collision happens earlier, or a delay. And so it's an example where you can indeed, if you so want to, do this kind of studies nowadays. So now it gives me back to kind of trying to come back to the beginning. So in general, why would you want to fix? Either using the first trick or the second trick. And this is a delicate two-step dance that I have to say. Suppose you have a theory that is seemingly well-behaved if you choose data in here. So going back to Tesha's question, so if you're thinking about a regime, let's say we're only going to study regimes very close to the ones that satisfy the stability of Minkowski, you could imagine adding operators there that as long as they stay sane, sufficiently put, then everything should be fine. Because after all, my curvature will never be large. I know that GR is taking flat space or a small perturbation of flat space-time into flat space-time. If I put sane operators, then that should stay the same. And so you could imagine then trying to explore that theory. You put that, you make a numerical code in your computer, but then what you're putting is data here, but you're also sourcing a little bit somewhere else at high frequencies because your grid has a finite representation, and that's continuously feeding high frequencies. And that can make the problem just blow up in your face. And it's really not letting you study this, which is what you wanted to study. It's the superfluous introduction of high frequencies that shouldn't be there in the first place, but are there because of the tool that one is using that is making this blow in your face. So if you now have a way to control kind of the behavior here, then you can ask genuine questions of whether something that starts here stays within the domain of applicability or wants to move in this direction. And if it does move in this direction, then we're in trouble. And this works for all these cases. So I guess, well, let's see. Well, we're coming to an end. So, but now I'm going to go crazy. So I'll describe this. So if we look at this waveform, I'm not sure what you thought when you first saw it. I think when I first saw it, I saw it first twice. The first time was when Franz was finishing his numerical simulations. He happened to be visiting me where I was working. And I remember well because my daughter was born the next day. So I was looking at this. He showed me his waveforms, and I said, oh, shoot, I'm out of a job. I need to start doing something else because these waveforms are very simple. Then, I don't know how many years later, maybe 10 years later, we were with Matthias in an undisclosed location. We happened to see a copy of the paper that may or may not have been published already. And we saw this waveform. And the same thing, we're saying, oh, this is very simple. So we can draw many, many conclusions out of this, and I'll draw one in particular just to have fun towards the end of the lecture. So one thing we're seeing here is that several observations. So we have a system that's going around. It's being driven by the two objects that are going around. They have an orbital frequency. We look at the waveform, and that's the frequency we see. We don't see any other frequency, any significant frequency. we see a structure, an angular number structure, L equal 2, M equal 2. We don't see anything else. And so then you could ask, well, eyeballing here, the curvatures don't really get much larger than the ones that are involved in here. And then after the merger takes place, the curvature actually is even weaker because you form a larger black hole, right? So if you're modifying your GR with these extra higher order operators, it seems like it's a very sensible way to think of accounting for deviations because nothing strange is happening here. So I don't know how many of you got in the pool the other day, director's pool. I mean, you should have, because how many chances you have to get into the director's pool. But if you play around with your feet, I don't know how many of you have done this. You go around and then you're driving with their given frequency and you see these vortices that form. They're smaller vortices. You put energy in a frequency here and in a given length scale, and then these smaller length scales show up. Why is that? It's because the theory is nonlinear. Why is that? Why do we have such a simple thing if we're dealing with a nonlinear theory? So then one option is to say, well, I mean, the theory is really not very nonlinear. It's essentially what we know in Newtonian theory plus a little bit. That's well and fun. The other thing is we have this, for us, cosmic censorship is also hiding away all the nonlinearities into the black holes, and we never get to see them. So black holes are amazing then. Black holes are hiding singularities, they're hiding nonlinearities. Somehow I have a problem with that. And that might make me get into trouble because then I end up dreaming things. So I'll tell you what I'm dreaming. So one thing is that to say careful, we may be too comfortable thinking always in linear terms. Like we, on many fields of, many branches of physics, have gotten tons of mileage by looking at the harmonic oscillator, the hydrogen atom, the black holes, and perturbing linearly on top of that. But if you're truly asking a nonlinear question, are we using the right strategy? This is like me going to a corrupt politician and asking, are you stealing? Of course, he's going to say no. It's going to take me a long time through that inquiry to try and find if his bank account has increased in a fundamental manner in the past year. So we may have to use a different set of tools. There is one field, fluid dynamics, that cannot make much headway by linear analysis. And so they typically end up with using a different set of tools to study problems. And so I'm going to borrow some of them and see what we can make up and then make a story. So in their case, something they do, because they have a very complicated system of equations, is they set up steady states. So you take a field, they take your problem, you go to your director's pool and you start moving your feet for a very long time. You're injecting energy, and then you look at what happens with these vortices you're forming. You keep track of them. And what you see is that if you're forcing energy, for instance, somewhere there, in the 3+1 case, then you see that you end up generating a spectra of energy that decays in this way, and it has this famous -5 theoretical Kolmogorov scaling. And they can do numerical simulations and confirm that. Then you can try and do the same thing in 2 dimensions, and you inject energy here, and then you realize that something else happens. There is this Kolmogorov scaling is not going towards the UV as in the 3+1 case, it goes in the opposite direction. And then there is some energy that does go to the shorter wavelengths, the UV, but in a much steeper way, and this is something that Krajnen recognized in the 50s. And this is the understanding of this is what underlies that. Right? So this hurricane couldn't care less what's going on at the small scales where energy is dissipated. This has grown to very long scales. So this is driven by the nonlinearities in the system saying, no, you're not going to go that way, you're going to go in the opposite way. So now we're going to try and take a page of them, and this is something that Zizhen Ma has done, and then try and see what we can learn. And this will allow me to say a few more things. So suppose you take your computational domain. You're going to put not a square box, but a spherical box. You're going to have a black hole in the middle to begin with. In the spherical domain, you're going to put boundary conditions, and the boundary conditions in general theory are non-trivial. So what do people do nowadays? And I'll tell you, they do one of these many things. One is you put this boundary as far as you can in this boundary, then we know what to do, right? We said, look at the characteristics, everything that is outgoing, let it go. You have to give boundary conditions on the only thing that comes in. Well, in principle, you can give something. Of course, we make a mistake because we know in general relativity, any wave that goes out will backscatter of the potential and come back in. And so we don't know what to put in there, because if we knew exactly what to put in there, we would have solved the problem already. So people put different things there. They all make a physical mistake. It's consistent, or consistent to a point. We have a theory that is constrained. So not all the modes that we will recognize from the hyperbolic analysis, the characteristic analysis that comes in is free to give. We know that there are constraints, and we need to involve the constraint to know what's a subset of things we can give, and the other ones are completed by the constraint satisfaction. So that's one of the things that people do. Another is the one that I briefly mentioned the array. You can try and compactify, bring this boundary to infinity. There you're running out of resolution, but you introduce dissipation and you basically obliterate everything is there, so you don't have stuff coming back in. And then the third one is to say, well, then you can match to an outgoing, maybe a characteristic decomposition, go all the way to infinity, and then do that. One of these three things are done nowadays. We're going to play one of those tricks in here, but in a different way. We don't care about really doing what is a true physical problem of two black holes that are coming together where the boundaries are sufficiently far and we're putting the backscatter of that radiation that comes in. We're just trying to see what is the nonlinear response of the black hole. So at this boundary, wherever it's here, we're going to use these constraint preserving boundary conditions to truly give initial boundary data to the minimum amount of data that we can give there. The rest is given by the constraint. And if there is any piece, any gravitational wave or any signal that wants to get out, we're going to let it go out. So we're using what we said about exploiting the characteristic structure of the system. But at the boundary, we're going to drive. We're going to be your feet in the director's pool and doing things in different ways. We're going to steer with some frequencies. These frequencies are up to your choosing. Depending on the frequency you choose, if it is too long or too short, in one case it's like it doesn't see the black hole. In another case, it all falls into the black hole. We're just going to look for something that's commensurate with the size of the object that you have in the middle. We're also going to choose an angular momentum structure that is either 2 or 6. So one is to have the minimum angular structure that a gravitational wave can have, and the other one that has a larger one as far as L is concerned to try and contrast. And then we're going to have an amplitude that is up to our choosing to try and check what happens as we go around. So this is an example of having a tool that you built it for doing a binary black hole collision, but along the way you think of an interesting question and you might as well exploit it. So I'll tell you what happens. So you do this and you start kind of hitting the boundary with these waves. They're coming in. Immediately, so of course you have a nonlinear set of source terms there. You have the field to the square, to the cubic, etc. And so what you see, so this is a case where you drive with an L equal 2, small amplitude, let's say. They all grow, and immediately if you hit with omega, then you see that there is also energy in the 3 omega, 2 omega, and 1 omega. We're going to look into this in detail. If the amplitude is sufficiently small, then these things just stay there. There are modes that got some energy because you're giving energy. They're also losing some energy away to infinity or to the boundary. But essentially, you just generate a steady state. The reason I'm not showing the rest of the plot is because now I'm going to show you what happens if you increase the amplitude. This, for small amplitudes, is what you see. And then we'll show you a different plot in a second. Instead, if you also then drive with L equals 6, you're putting energy in the L equals 6, and through nonlinearities, you populate an L equal 4, and you populate an L equal 2 in, say, in 2 omega. Now you increase the amplitude here, and you keep watching what happens here. So when you increase the amplitude, this energy that was in 3 omega doesn't want to stay there. It wants to come down to the 2 omega, doesn't want to stay there, it wants to come down to the omega. So it just went down in frequency. Didn't want to be a 3 omega, didn't want to be a 2 omega, wants to be a omega. Remember, I was asking the question, we have these two black holes that are going around each other. they are generated in omega. Why don't I see higher frequencies? Well, maybe because in nonlinearity is the nonlinear terms. They don't want to do that. They want to go back to the omega. In the L equals, when I do the L equals 6, then you see what happens in the omega. And then initially you have essentially nothing in the 4 and the 2, but as time goes on, the 4 grows, the 2 grows a lot more, and then you have this kind of spectra. This happens always, regardless of the amplitude of the pumping that we do. Because you can argue there is always room to the bottom. If I have energy in the 6, I can go to 4, I can go to 2. That's a minimum that I can support. This one, however, no, needed a sufficiently strong amplitude. So there is a separatrix. Small enough amplitude, nothing interesting happened. Large amplitude, something interesting happens. This is like the laminar versus turbulent separatrix. This is the same information in a different way. So this is for different values of the amplitude. This is the L equals 6. When you drive with L equals 6, you can essentially see, regardless of the amplitude, always the same thing. But if you have the L equal 2 and small amplitudes, this is what I was showing, this kind of constant kind of behavior. But as you increase, then you begin to see this growth rate and then this decays. And you can understand this because you have the amplitude, and then you can ask, how does this amplitude and the saturation points when they turn around depend on the amplitude? And then you can realize that there are two instabilities, that one involves 3 modes, the other involves 2 modes, that are driven this problem. And so I'm going to tease as a final thing is maybe that simplicity of waveforms that we see is precisely the nonlinearities. It's not that the problem is simple, the problem is extremely complex, but just that complexity builds up into the simplicity. Just a final message. Well, numerical relativity, that's what I was supposed to talk about. So numerical relativity is relativity exploiting computers. It's one tool of many. It's a particular tool that is quite apt to explore regimes that are not tractable by other means. But hopefully, by doing so, you find hints that there are easier, better, cleaner ways of doing it, and the tool was a means to an end. There are many problems of interest, from practical and timely ones. For instance, gravitational waves for data analysis, for encoding information efficiently, etc. But if you're really thinking about gravitational waves and the binary black hole problem, so nowadays, perhaps the biggest challenges are how to deal with the large mass ratios, the high spins. And if you saw the paper that came out last week, showing a particular event that's really railing against the boundaries of everything that has been explored, you can see how challenging it is. There are lots of questions in that paper that were not addressed simply because we don't have data simulations accurate enough to in that regime. And of course, the regime of high mass ratio is still far. It's waiting for a new clever idea. Hopefully, one of you will be the one that brings it up. But with that, I'll close it here. Thank you.
About the last thing you talked about the driving the black. I don't think I understood everything. So it's like me staring at a Clarkson column, painting and trying to make sense of it. So in the binary problem, you have to think that the orbit's frequency is increasing. And you're saying that if you stir the hole, the frequency, it wants to go to lower frequency. So it is stable because at later times, the things don't, they keep going down. But we could imagine a system like, kind of like the AMCAN system where.
Like a what, sorry?
AMCAN. These are AMCBN systems that Neil Cornish talked about, where mass transfer is causing the orbit to widen. So then over time, it has an inverse check. Then could we have a thing where the nonlinearity talk in that sort of? I'm just saying words.
So yeah, I'm not sure what to say there. So the only thing so from that point of view, what this is saying is I'm driving with some frequency. If we believe this analogy or this, and I have to say something else I forgot to say. If we're driving with a frequency, it seems the system doesn't want to go away from that frequency. So if I drive these in this way and then I begin to go backwards, fine, it will just want to stay in that frequency. So if it goes up or down, so they're saying that smooth kind of chirping behavior. You could think of it as just energy staying there with a small variation that is due to the energy that's being lost, but you can always kind of think of a sequence of just quasi-steady state in that behavior. The other thing I forget to say is that we can take a black hole away, and the same thing happens. So there's nothing special about the black hole. So if I leave flat spacetime to begin with, C-Shank sense energy, some sort of condensate forms, because it has a little bit of self-gravity, so it stays together. Of course, if you stop the driving, it will dissipate away. And so you're replenishing whatever is losing by what you're sending in, but there is some sense of some amount of effective mass density in there, or energy density. And you see exactly the same behavior. Of course, the amplitudes are smaller. Like black hole kind of energizes this process or makes it even stronger, but it's not the black hole, it's the self-gravity. Sorry, say again?
Beyond GRFT, how do you test those in practice with the detectors we have? Because do I have to go away from catalog for every one of them and then test models?
No, excellent question. Yeah, so what do we do? So in fact, we have a paper that came out yesterday, I think, where so the first thing was, the ability to explore a field allows us to kind of say or reinforce the point I just made. The binary black hole system does not explore high frequency, does not explore high curvature. What we see is that it doesn't send energy to high Ls, so it doesn't explore short wavelengths. And if it doesn't do that, then these corrections, as long as the corrections to GR are captured by this EFT route, then the EFT route adds higher curvature components. So those are not going to be large. So the modification of the waveform will be very subtle. Now, there are infinite number of these theories. Well, infinite might be a bit too an exaggeration, too large of a number, but it's a very, very large number of theories. There's no way we're going to explore them all, or there's no way we're going to have a sufficiently dense catalog to do it that way. But we can track the main messages that they will have. So one of them is that every theory, so let's see, I have it here. Let me put it. So every theory will have a coupling. That coupling introduces a physical length scale. So something and that physical length scale scales in a particular way. With this one, this is R squared, so this should be like this length scale to the square power. The gravitational wave doesn't have any dimensions, so the difference between the waveform in this theory and any of these theories on GR will be modulated by a ratio of this new length scale divided the total mass of the system to a given power. So these are lessons for the gravitational wave data analysis. They say, well, look in the residual for things that are modulated by L over M to some power. If you detect or you can extract what that power is, then that will kind of home in on the subset of theories that are consistent with that. And this paper that we put out with Suvendu, sitting there, Giri, and Laura Bernard and Ricardo Sturani, are taking a page and running with this. Then you can use PNEFT or NRGR kind of calculations in the spiral to say this is how any of these theories, depending on some assumptions, will impact and in what order. And in particular, one of the main kind of lessons from that work is to say, you're going to have something that scales with the mass of the system in a particular way. So imagine having a number of events that allows you to get the power. But also importantly, the level of the PN order gets affected. So if you can sort of confidently say any PN order lower than 5 has not been changed and is 5 PN and above, then you at once can say there is no extra degree of freedom. And it's just a purely curvature correction. And vice versa. If it modifies a low PN, then you say, well, there is an extra degree of freedom. And because it's scaling with this power in the mass, then it's this small set of theories. And then we can go study those in particular. But it's then in our way of presenting this it's going to be 100% data driven.
The rotating black holes that Einstein occur at ambiguous boundary conditions.
I didn't say that. I think you know the paper better than I do. Yes. So you're giving me no. So that one, Let's see, I don't know enough about that theory. So what people have proven recently is initial boundary value problem seems to be under control. And so it's waiting for someone to study. I'm not brave enough to go there, but yes, so. Okay, so I think as the last speaker, I should be asking everyone to thank the organizers. It was a great school.